and I'm cold because of this class and I don't know what to do with it. So now you have to get used to this new voice. Okay, today we're going to talk about Coq as the programming language. Basically, Coq's programming language is a functional programming language, and we're going to see some of the very basics of this language. Now, if you've done any kind of functional programming before, everything I say in this session is going to be trivial. Okay, so let's start. First of all, I have to say that the credit for all of these examples goes to Michael Clarkson. I'm just plagiarizing his examples. So here's one thing that we often do in Coq. We write check and then some expression. And what this does is that it performs a type check. So it tells you the type of that expression. For example, true is of type bool. Okay. Now, one question would be, how do we define new types? So you can think of it as the same way that we use a struct in C or a class in C++ and Java. So here we can actually define new types inductively, and you will see what I mean by inductively very soon. So let's say I want to define a new type called day. This is how I define it. I say that day is a type, and then I have to give a definition for day. And this definition is going to consist of a bunch of constructors, and it's basically very similar to the way that you define a grammar. So for example, in this case, if I'm talking about days of the week, I'm going to say that a day is going to be either Monday or Tuesday. Someone's trying to come in, okay, or Wednesday or Thursday, Friday, Saturday, or Sunday. And remember, all of our commands end with a dot. So this is how I define a day. And as you see, when I execute this, it says that day is defined and some other things are also defined. Okay, so we will get back to these things and what they are at some point in the future. But for now, all you need to know is that this is how I define a new type. And this is actually very similar to how you define an enumerative type in C++. So when you define an enum, but we will see that this inductive definition can actually be more powerful than that. Okay. But now let's say I want to define a function. How can I define a function? Well, I can use a definition. I can say, let's say I want to have a function that gives me the next workday. And the way it works is that it gets some day D. I like to put underlines, but you can just do without underline as well. You can give it whatever name you want. And you have to say what's the return type, and the return type is also day. And now you have to define the function. Now, the way we usually define a function like this is that we use pattern matching. And again, if you've done any kind of functional programming, this is going to be very similar. So this is what I'm going to write. I'm going to say match d with, and then basically I'm going to do a casework. I'm going to say if the day is Monday, return the next day, which is Tuesday. If D is Tuesday, return Wednesday. If it's Wednesday, return Thursday, and so on. But I'm doing next workday, so if it's Friday, I'm going to return Monday. If it's Saturday, I'm going to return Monday, and if it's Sunday, I'm going to also return. Okay. Oops. Yeah, and every match should end with an end keyword. Okay. So this is now defined, but here's the thing. Whenever you're doing this kind of pattern matching in Coq, you have to make sure that you consider all the possible cases. So this is supposed to be a function that maps days to days. So for example, if I remove this line, if I don't have Thursday in there, you see that it says the pattern matching is not exhaustive. And I get an error. Okay. And I mean, one other thing I can do is that, well, I can say that all of these things are going to be mapped to Monday. So at this point, I'm just going to write it like this. So this just, it's like an if, else, if, and so on. So it tries to match D with Monday, then it tries to match it with Tuesday, and so on. And the matches always go from top to down. So when it reaches this point, everything matches, and then it just returns Monday. Okay. Now, how can I actually compute using this? Well, I have the keyword compute for that. So I can write something like this. I can say compute the next workday of, let's say, Wednesday. And it tells me that it's Thursday and its type is a day. Okay. And I can also do it in a nested way. So compute the next workday of the next workday of, let's say, Tuesday. Okay, and this is Thursday, which is a day. Okay, very easy until this point. Another thing that we do, we've already seen theorems. So another name for theorem is lemma, and another name for lemma or theorem is example. So in Coq, all of these things are the same. Example, theorem, lemma, they mean the same thing. But we usually use example when we want to write a test. So I'm going to have an example called test. And what this example says is that I want the next workday of the next workday of Tuesday to be Thursday. Okay. Now, did you see what happened there? As soon as I wrote an example, now I have to prove it. Because examples are basically the same as lemmas and theorems. So I'm going to start a proof. How would you suggest I prove this? Yes. So there is a tactic for that, and that's called compute. So if you just write compute as a tactic, it will do the computation. And basically, it computed the left-hand side. Look at the left-hand side here. It computes it, and it says, okay, now you have to prove Thursday is Thursday. Okay. But if I want to just do one step instead of computing everything, I can also write simple like this without the E. It stands for simplify, and it tries to simplify. And in this case, I mean, simplification gives me the same thing as computation. So let's say I write compute. How do I prove this? It seems to be very trivial, but no, we don't have any assumptions here. Yeah, so this is the reflexivity of equation, right? So I can just write reflexivity and it understands. Of course, you can also do auto. Okay, but one point is that actually reflexivity is quite smart. So even before doing compute, I can write reflexivity and it does the compute itself, and then it says it's proven. But okay, this makes more sense for a human. So I'm going to write it like this and Qt. Okay. Now let's define some other things. I'm going to start a new module here because I'm going to define things that are already in Coq standard library, and I don't want to have clashes. So let's say I want to define Booleans. So I'm going to create a new module called myBool. And let's just define Booleans and operations on Booleans. So I will have an inductive type again. I'm going to call it bool, and it's a type. And I'm going to say it's either true or false. Okay. And now bool is defined. So now I want to define some operations. Let's say I first want to define a unary operation, which is just negation. So I'm going to define Boolean negation, neg-b. And this is an operation that gets a Boolean and also returns a Boolean. Okay, how should I define this? Yeah, so match B with, and it's just like if B is true, return false. And if B is false, return true. And you have to always remember that you end your match with end and you end your command with a dot. Okay, so now negation of B is defined. So here's the thing. If I write check neg B of true, okay, what I want you to see here is that it doesn't actually compute neg B of true, it just checks the type. Because it knows that true is a Boolean, and so neg B is also a function that maps Boolean to Boolean, so neg B of true is going to be Boolean. But of course, if I write compute neg B of true, this will give me the answer, which is false, and it will tell me that it's also a Boolean. Okay. How do you define, let's say, conjunction and? So let's say I want to have and B. How should I write this? Boolean and. So I need two parameters now. I need a B1, which has to be Boolean, and I need a B2, which should be Boolean, and I'm going to return a bool. And okay, what's the definition? How would you do this?
B1, B2 both are true, then it's true, otherwise false.
Right.
Match both, match B1, B2 both.
Can you do it with one match? So let's I will write it the way you said to, but let's first match B1. And I'm going to say if B1 is false, return false. And if B1 is true, what do you want to do then?
B2.
Yes.
Oh, it works.
Okay, yes, this works. But this is basically an AND operation that does short circuiting, right? Because if B1 is false, it doesn't even look at B2. Okay, let's do a different definition. And by the way, I can write the two parameters like this. I don't need to write them like that. This saves some space. And I'm going to return a Boolean. Okay, I can actually have nested matches. So I can say match B1 with, if B1 is false, just false. And if B1 is true, then let's do another match. Match B2 with, and if B2 is true, then true. If B2 is false, then false. And then I have to end both of my matches. Okay, this looks a little bit stupid. But anyway, this is like another way you can write this function. Okay. But what if I don't want to have short circuiting? What if I actually want to look at both values as you suggested. So let's write it like that. So I have B1 and B2 that are Booleans, and I'm returning a Boolean. And I can do this. I can match a pair, basically. I can write match B1, B2 bit. Okay, what are the cases? So I want to say if it's false, false, return false. If it's false, true, return false. If it's true, false, return false. And only if it's true, true, return true. Okay, so this is another way of defining that. But actually, this wasn't too interesting. So let me do another case where I do the match on the pair B1, B2. But let's say I write it a little bit smarter. So I'm going to say match B1, B2 bit. And then basically I'm going to return true only if both of them are true, right? So I'm going to say if it's true, true, return true. And in any other case, return false. Okay, this is another definition. I could also write this like this, but it doesn't really matter. Okay. And then, of course, I can also do computations with this. So I can say, what is the AND of true and true? And for of true and true, and it's true. And yeah, I can also combine them and call as many functions as I like. Let's also define disjunction or. So let's say I have B1 and B2 that are Boolean, and I want to return a Boolean. So I'm going to, again, do a match. And I'm going to say that if both of them are false, I'm going to return false. And in any other case, I'm going to return true. Okay. So let me do another example. I'm going to call this one test 2. And I want to say if I compute the OR of true and false, that's going to be true. Okay, how should I prove this?
Compute reflect and then reflect.
Yes, it's exactly the same as before. We first do compute and then we do reflexivity. Okay, another thing that I can do is that I can actually define infix notation. So I can write something like this. I can write notation X and Y. And I can say that whenever I write something, what I actually mean is, let's say, and before of X and Y. Okay. And so if now I say print this, print X and Y, it will actually tell me that, okay, the name of this function is actually and before. It's a function that takes two Booleans, and this is how it works. So it matches and so on. This is like just the body of my function. Okay. Now, another thing that we can do sometimes is that we can just leave part of our program incomplete and come back to it later. So I can have, let's say, a NAND operator, negation of AND. And here, instead of actually defining it, I'm going to leave it like that, and I'm going to say admitted. So it's just something that I can come back to and finish later. If you have this word in any of your homeworks, you're getting a 0. Okay. Because this is also something that I can do for. Okay, so actually here I can just define land very easily, right? So it's the negation of the AND of B1 and B2. Okay, and this was called neg B, and this one was like AND B4. Okay, now I have NAND. Okay. Now, one thing that you have to understand is that everything has a type. So I can write things like this. This is again type checking. It just tells me that the type of true is bool. But even these functions, they have types. So I can say check NAND B. And it basically tells me that this is the type of NAND B. So the way we read this is that this is a function that takes 2 booleans and gives me another boolean. But actually the way Koch is thinking about it is that it's a function that takes a boolean and gives me another function that maps the second boolean to the final result. Okay, so that's how it thinks of it. But anyway, that's fine. Let's define some more interesting types. So let's say I want to define a type for color, and let's say I have only 3 colors, red, green, and blue. So I can just define it like this. And okay, I can now define another type. Let's say I call it color. And here's the thing. I say that my color can be white, or it can be black, or it can be one of the previous colors that I had. But I'm going to write it like this. I'm going to write primary and PRGB. Okay. What does this mean? Well, the first 2 parts are trivial. So a color can either be white or black, or it can be just the color primary. But if it's a color primary, it also has a parameter. And the parameter is some P that is itself of the type RGB. Okay. So now if I write check white, this is a color. Black is a color. Primary on its own, it's not a color. Okay. But if I do primary of red, that's a color. So you see, this is a new type of constructor that allows you to have a parameter of some other type. So again, primary of blue, this is a color. So, okay. And also, I don't need the parentheses. I can just write it like this, of course. Okay, let's say I want to have a function that basically tells me whether a color is black or white. So I'm going to call it monochrome. And it takes a color C, and it returns a boolean, and it should be true if the color was either black or white. Okay, how would you write this? So this is again about pattern matching, right? So I can say match C bit, but now what are the patterns that I have to cover? I have to cover all 3 of these constructors here. So I have to say what happens if it's white. I have to, let's say, return true. What happens if it's black? And what happens if it's primary with any parameter? I should return false. Okay. That's it. So the point of this example was to just show you that you can have more complicated patterns and you can do pattern matching on them. And of course, you can also have more complicated constructors when you're creating a type. Okay. And of course, we've seen how to define variables before, so I'm not going to go over that. Let's define natural numbers. I'm going to create a new module here again because actually I have to end the previous module. What was it called? Just my bool. So I'm going to write end my bool. Again, natural numbers are already defined in Coq, but I want to define my own natural numbers. And I'm going to define them pretty much the same way that they're already defined in Coq itself. Okay. So let's see. I'm going to have my nat, which are my natural numbers. So let's say I want to define a new type nat. It's a type. And I want it to be the set of natural numbers. How would you define this?
Natural number.
Yes. So if you've passed the course in number theory, you should know about Peano's axioms. So basically, there is a particular natural number 0, right? And for any natural number, there is a successor. There is the next number. So I can say that my natural numbers are either 0, which I'm going to show with the capital letter O, okay? Or it's the successor of another natural number. And how do I write this? How do I say it's the successor of another natural number? So look at this definition here. Here we had a case where one of our constructors could take some parameter. And here I have a constructor S, and I can say that it can take a parameter N, but in this case, that parameter is of the same type nat. So I'm giving an inductive definition. I'm saying every natural number is either O, which is my way of representing 0, or if it's of the form S of N, where N is another natural number. Okay. So now I can check the type of O. It's a natural number. What is the type of S of O? This is also a natural number. This is basically how I'm representing 1, right? And then 2 is basically S of O. That's how I represent 2, which is also a natural number, and so on. Okay. Now, how can I actually define some operations here? So let's say I want to define a predecessor operation. So let's say I want to define pred. And what this does is that it takes a natural number n, and it returns another natural number, and I basically want to return the previous number. So I want to return n minus 1. Of course, if it exists. If it doesn't exist, if n is already 0, I just return 0. Okay, how would you write this?
First line. Define the 0 and 1 separately, and then define the other numbers recursively.
We don't even need recursion here. We will get to recursive functions, but at this point, I don't need recursion. So let's just do a pattern matching. So let's say match n width. Now, what are the cases that, okay, actually, let me call this something else. Let's call it A. So let's say match A width. And what are the cases that A can have? According to its definition, according to the definition of the type NAT, it's either O or it's S of some N. So it's either O or it's S of N. Okay. So what do I want to return if A is O? I want to return O itself because basically this is 0. It's technically not well defined because I don't have a natural number smaller than 0, but I'm going to just say it's 0. What should I return in this case? Yes. And now I can do computations with this. So I can say compute the predecessor of S of S of S of 0, and this is basically 3. So predecessor of 3 should be 2. Oops, I should write O, not 0. And as you see, predecessor of 3 is 2. Okay. But I'm going to end this natural numbers module, and I'm just going to use the NAT that is already defined in Coq itself. So I'm going to do this. And I'm going to do the same thing for Boolean. And the reason for that is that I can now basically use normal numbers, but I just want you to know that they're defined like this. So if I say check O, it will tell me that now O is the number 0. Okay. And check SO, that's the number 1. Check S of 1, that's the number 3, and so on. So if you import the naturals from Coq itself, it at least shows them in a nice way in the decimal representation. Okay, but let's say I want to define another function, and I basically want to do -2. So I have a particular number A, which is a natural number, and I want to return A -2 if it exists, and if it doesn't exist, I want to return 0. So how would you do this? Yes. First of all, can you do it without match? We can just use the definition of pred, right? So we can say this is the predecessor of the predecessor of A. Okay. But if I want to do it with match, I say match A with, and now there are several cases. Either it's O or 0, in which case I want to return 0, or it's SO or 1, in which case I want to also return 0, or it's of this form, S of N, in which case I want to return N. No. Why should it be A? No, so A is the parameter here. I'm saying if A is of this format, if A is equal to S of N for some N, return that N. Okay, so I can say compute -2 of 6 now, and it will give me 4. Okay. Now, what if I want to define a function that tells me whether a particular number is even? So let's say I have a number A, and this is a natural number, and I want to return a Boolean, and basically I want to say whether it's even or not. How would you define this?
true, it is 1 returns 4, otherwise returns is -2.
Sure. So I can say this. I can say match A with, and then I can say if it's 0 or O, return true. If it's 1, return false. And if it's of the form S of n, return what?
Either of n.
Yes. Well, actually, I have to change this because even is already defined, so I'm going to call it my even. Okay. So let's say my even of n. Okay, this is the problem we have. It says the reference my even was not found because, well, we're just defining it and we cannot use it in its own definition. Yes, so if we want to define a recursive function, we have to use this keyword. We have to use the keyword fixed point. And if I write it like this, then it will work. Okay, and look at this. It says that my even is defined, and it's also recursively defined, and the recursion is on the first argument. Okay. I could also write it like this. So I could have the same function, and I could just say, if it's 0, return true. Otherwise, if it's of the form S of n, just return the negation of my even of n. Right. This would also work. But now when I've defined even, I can also define odd. So I can say, and by the way, I'm adding my because these are already library functions that are defined. So if I want to say whether A is odd, I just say take the Boolean negation of my even of A, right? So I don't need to give a fixed point or a recursive definition for odd. Okay, so let's do this. I want a test which basically says 4 is not odd. How do you prove this? Yes, let's just do compute. And you see, when I do compute, the left-hand side just becomes false. And then I can just do reflexivity. Okay. Now I want to define addition and multiplication and so on. And the problem is that they're already defined. So I'm going to create a new module, and I'm going to define it in that module. So let's say I want to define addition or just the plus operator. And let's say that I have n and m, which are natural numbers, and I want to also return a natural number. So how would you define this? Remember that our definition of natural numbers is just that it's either O or it's S of n, where n is itself a natural. Sure. Let's do a recursive definition. Let's have fixed point.
If the ball n is 0, n is O, so you should match only O and then return n. Otherwise, they'll return plus n minus 1 and it's successful.
Yes. So I can do it on either n or m, but let's say I do it on n. So I say if n is 0, you just return m. And if n is s of some n prime, then what do you return?
S of plus and prime n.
Yes. And that's it. So now I can say compute plus 5, 7. And that's 12, which is okay. How about multiplication? So let's say I want to multiply n and m, which are natural numbers. Yes.
If n is 0, just 0. If n is Sn prime, then we should return 12 of n multiplied of n prime n.
Yes. If n is 0, we just return 0. And if n is the successor of some n prime, so n is n prime plus 1, we're just going to take the multiplication of n prime and m, and we're going to add m to it. Okay? And that's it. So compute 7 and 8, it's 56. Okay, but the point I want you to realize is that I could have defined it in many different ways, right? So for example, I'm doing this matching on n for both plus and mult, but I could do them on m, right? But actually, from Koch's point of view, multiplication is now this far. For Koch, it actually matters which definition you use. And you will see this a little bit later when we want to prove some stuff. Okay? So let's define the minus operator. Let's say I have n and m, which are natural numbers. How do you define this? Yes. Okay, so let's do a matching on both n and m. Okay. What are the cases? So I basically want to see which ones are 0 and which ones are not 0. So first of all, if n is 0, no matter what m is, I'm going to return 0. Okay. What if m is 0? So I don't know what n is, but m is 0. If m is 0, I'm just going to return n. And now the remaining part is that none of them are 0. So I have s n prime and s m prime. So n is of the form s of n prime, and m is of the form s of m prime. What should I return in this case? Yes. That's it. That's the recursive definition of minus. Okay, let's say I want to define greater than or equal to. N and m are natural numbers. I want to return a Boolean that basically tells me whether n is greater than or equal to n.
M is zero, then returns true.
Mhm.
So
Okay, so here's actually what I can do. I can use the minus operator. And I can say take n minus m. Or actually, sorry, take m minus n. And if m minus n was 0, then return true. Otherwise, return false. Okay, because that's the way my minus works. Okay. If m is smaller than or equal to n, m minus n is giving me 0, so I'm using that. Okay, and now based on this, I can also define equality, basically. So I can say, I want to give you several definitions of equality. So n and m are equal. When are they equal? Yeah, so I can take the Boolean and of two things. The first one is that n is greater than or equal to m, and the second one is that m is greater than or equal to m. But what if I just want to define equality recursively on my own? So let's say I don't want to use any of these previous ways. So I just want to do a matching again. I can write something like this. I can say, do a pattern matching on n and m. Okay, what are the cases? Either they're both 0, in which case you return true, or the first one is 0 and the second one is not 0. Okay, I'm saying not 0, but here in the pattern I'm writing anything, and the reason for that is that the patterns are matched in order. So if I'm here, it means I didn't match this previous pattern. So if n is 0 and m is not 0, then they're not equal. Similarly, in this case, they're not equal. And the other remaining case is that each one of them is the successor of some other number. So n is the successor of n prime, and m is the successor of m prime. What should I do in this case? Yes, just return whether n prime and m prime are equal, and that's it. Okay. I could also write it a little bit differently. I'm just giving you all of this so that you get used to writing these kinds of programs. So instead of doing a matching on both of them at the same time, I could first do a match on n, and then I could put a matching on m nested inside this. So I say if n is 0, then match m, and if m is also 0, return true. Otherwise, if m is, let's say, s of some m prime, return false. End of this matching. Back to this. If n is s of n prime, again, do another match on m. And if m is 0, return false. If m is s of m prime, return whether n prime and m prime. Okay. I did this just so that I can show you that you can have nested matches like this. Okay. Anyway, all of these are already defined. So if I just close that module, but if I write, for example, or B, this is already defined. This is the Boolean or operator. Or another way of doing this is Yeah, one other thing that I want to tell you is that just the same way that in a lot of programming languages you have different notions of equality, this is the case here as well. So let's say I write check 2 equals 3. So what is the type of this expression? The type of the expression 2 equals 3. It's actually a proposition. Right, so if I write it like this, Coq basically thinks of it as the proposition 2 equals 3. But if I write it like this, with a question mark, then this is a Boolean. Okay, so if I say compute 2 equals 3, it just gives me 2 equals 3, which is a proposition. But if I say compute 2 equals question mark 3, it gives me a false, which is a Boolean. Okay, and so we have the same kind of thing for inequality and all sorts of things like that. But let's finally prove some theorems. So this is the first theorem I want you to prove. I want you to prove that for all natural numbers n, 0 plus n is equal to 0, is equal to n, sorry. How would you prove this? Okay, first of all, we have this for all here, and we have to get rid of this, so we have to do intros. Or actually just one intro here. Oh, by the way, when you do intro, you can also change the name of your variable. So if I just do intro, it brings n up here into the assumptions, but I can write intro x, and then it renames it to x. Okay. So I want to prove that 0 plus x is equal to x. What should I do? Can I just do compute? Yes. I just do compute and it computes 0 plus x and it gets x. And now I have reflexivity. Great. Simple theorem. Now I can do the same thing for plus 1. For all n, that is the natural number, 1 plus n is the successor of n. How do you prove this? Yes, so again, I just do intros, and then I do compute, and I got the same expression on both sides, so I say reflexivity. Okay. Here's another very simple theorem. So I want to say for all natural numbers n and m, if n is equal to m, then n plus n is equal to m plus n. Try to get to QED on this. So of course I have to do intros first. But now this is the situation I'm in. I have the assumption that n is equal to m. So here's where I can use another really useful tactic, and this is a tactic that we use all the time, and it's just called rewrite. So if n is equal to m, I can replace all occurrences of n with m. And I can also rewrite in the other direction. So this is how we would do this. I would say rewrite h. And what I mean by this is that rewrite my goal based on h. Okay. And I can also give it a direction. I can give a direction like this. And you see that all the m's are replaced with n. If I do this, I could give it the other direction and it would do the other replacement. Anyway, so I rewrote my goal using H, and now my goal is very simple. Both sides are the same, so it's reflexivity. Okay. And let's see if I have a better one. Yeah, let's do this. I want to say that for all natural numbers P and Q, P times 0 plus Q times 0 is 0. Okay. And before I do this, I want to show you two things. Okay. I want to show you this one. There is something already defined, which is called mult NO. And as you can see here, it basically says that for all natural numbers n, 0 is equal to n times 0. Okay. That's one thing that is already defined. And another thing that is defined is mult NSM, which says that for all natural numbers n and m, n times m plus n is equal to n times s of n. So we already have these theorems or these lemmas, and they're already proven in the standard library. So using these two, can you prove this theorem? Can you prove that for all p and q that are natural numbers, p times 0 plus q times 0 is equal to 0? So what do we know? We know from this assumption or this lemma mult n 0 that anything multiplied by 0 is 0. So I want to somehow use that. First of all, I want to get rid of this for all and put them up there in the assumption. So I do intros, P and Q go up there. Now I say I want to do a rewrite, but I want to rewrite using mult n 0, right? So I say rewrite based on mult n O. What's going wrong? Oh, I forgot the direction. Okay, and see what happened there? So it found p times 0, and in mult NO, it knew that p times 0 is 0. So it put 0 for p times 0. And now I can do the same thing. I can say, do it again. And it does it again. And now I have to just prove that 0 plus 0 is 0, and I can just write reflexivity for this. Because reflexivity is smart, it does the computations. Okay. Here's the next theorem that I want you to prove. I want you to prove that for all natural numbers n, it's impossible that n plus 1 becomes 0. I want you to prove this. So again, as usual, we start with intros. So I want to ask you, what happens if I do simple here, if I want to try to simplify? Let's see. Nothing happens. It cannot simplify it at all. What happens if I say compute? For some reason, okay. So if I do compute, it does a computation like this, but this is not useful for me at all. This is much harder to prove now because it's just putting the definition. And yeah, so compute is not good. What do you want to do here? So let's think of a non-formal proof. Let's think of a proof that you would give to another human. Let's say that you want to prove that for any natural number n, it's impossible that n plus 1 is 0. How would you prove that? No, again, you're using some sort of understanding of numbers which is different from our definition. The only real definition that I have here, a natural number is either O or it's S of n, where n is another natural number. That's all I know about my natural numbers.
It's equivalent to say S of n is not equal to O, which is true.
Yes. So instead of n plus 1, I agree, we can put S of n.
Or to write that kind of thing.
But you want to say that it will never become O, but I mean, that's kind of obvious, right? So if you're S of n, it's not the same as O. I said, look at these things as grammars, right? So, where was it? Here is the definition. So if I want to say something is not O, it's enough to say that it's S of some n, because these are the different cases that I had here, and O is different from S. Okay. So basically, what I would really like to do here is to do a casework on n. I want to say either n itself is O, in which case n plus 1 is not O, or n is some S of n prime, in which case also the same thing. So, and we know that for doing casework, we used the tactic destruct. So I can write destruct, and I want to destruct n. I want to do a casework on it. Now, if I do this, you see that I will suddenly have two different goals. The first goal is where my n was 0 or O, and the second goal is where it was of the form S of n. But it doesn't change the name, so I don't like that. I can say destruct n as, and then I can give the names of the variables that I want to be used. So if I look again here at the definition, where was it? Okay, so this is the inductive definition of the type NAT. So it's either O or it's S of some new variable. So I can say destruct n as, and then O doesn't need any kind of parameter, but I can say call the parameter of the next constructor n prime. Okay, so this is now what I get. So basically I get n prime here instead of n. And additionally, if I want to also keep the relationship between n and n prime as an equation, I can do that too. I can write something like this, and it will add an equation E where it basically keeps the relationship between n and what I have here. So my first case when I'm destructing n is that n was 0, n was O. Okay. And this is what I have to prove. I have to prove that 0 plus 1 is not equal to 0, basically. Yeah, let's just do compute. And we do reflexivity, and that's it. So the other case is this. I want to show that S of n prime plus 1 is not equal to 0. How do I do this? Here I can try to simplify. And you see that as soon as I try to simplify, this is also giving me false on the left-hand side. So now why is that? It's because it computes S of n prime plus 1, and it sees that the pattern does not match. It's like, it's a pattern that starts with S here. This one is a pattern that starts with S, whereas this one is just O. So the fact that the pattern does not match tells it that it's not equal. And that's it. And we just simplify and we use reflexivity. Okay, again, very important that you have to understand Coq is very literal. It just knows the definition that you have given it, and it just uses that definition. Okay, let me do another theorem. For all Boolean values of B, I want to say that neg B of neg B of B is equal to B. So if I take the negation twice, I want to say that I get the same value. Okay. So again, I first do intros.
We can do case for
Yes. So if I just do compute, I get something like this, which is not great because that's how neg B is defined. Okay. But we can do a casework on B. So I can say destruct B, and let's say that I give the equation some name as well. I say equation is E. The first case is the case where B is true. And at this point, I can do compute. And then I can do reflexivity, or I can just do reflexivity because it does compute itself. And this is the second case, I can do reflexivity here as well. So as you're seeing here, we basically use intros, we use rewrite, and we also use destruct whenever we want to do a casework. Okay. Let's do one more theorem. I want to say for all B and C, and B and C is and of C and B. Okay. First of all, there's something interesting in the way I wrote this theorem. So in all the previous theorems, I always gave you the type of the variable that I was quantifying over. So I was saying for all B that is a Boolean, and here I was saying for all N that is a natural number. But here I'm just saying for all B and C. Now, the reason for that is that Coq is actually smart in this sense, and it knows that if I'm using and B on B and C, then B and C have to be Booleans. So I don't have to tell it that B and C are Booleans. Of course, I can, but I don't have to. Okay. How do you prove this? Okay, how do you do casework? What should I write?
Intros.
Okay, so I do intro. I actually have to do intros to take both B and C up. Okay. Okay, so I say destruct B, and I'm going to give the equation the name equation of B. So this is a casework on B. So the first one is the case where B is true. The second one is the case where B is false. Now I'm going to do, no, you cannot directly compute here. So if you just compute, this is what you get. Yeah, but this is actually nice. Look what happens when you do compute. So on the left-hand side, you had true and C, right? And when you do compute, you just get C. Because that's the way that and was defined. But for C and true, when you do compute, you get this. You get if C, then true, else false. No, it doesn't work that well. So reflexivity only works when they're literally the same on both sides, or they can be computed to be the same.
Are there any differences if C and if C the true else false? Not different.
Not in your mind, but for Coq, they are two different strings, right? If you think of them as strings, they're two different expressions, basically. Okay. Yes. So destruct C, and now in this case, we have reflexivity. Yes, and again reflexivity, and then again destruct C. Again, reflexivity and reflexivity.
Reflexivity.
Okay. So here's the thing. In cases where you have this, when you're applying the same thing on both sides of the proof tree, you can just put a semicolon, and so you can write it like this: destruct B, destruct C, reflexivity, and that's it. So what this says is that it says destruct B first, and then on all the sub goals do destruct C. And then on all the sub goals of there do reflexivity, so that I don't have to write it so many times. But now one thing that I want to show you here is, well, we had this theorem which basically said 0 plus n is n, and it was quite easy to prove it, right? So we had this theorem. We said for all n that is a natural number, 0 plus n is equal to n, and we had this simple proof. Now, what happens if I do this? If I say for all n that is a natural number, n plus 0 is n. Okay, so again, as a human, you have a lot of intuition and you think that these are the same, but these are not the same for Koch. Okay, so let's see what happens. If I do intro as before, and then if I do compute, this is what happens. And this is because of the way that plus was defined. So plus does a pattern matching on the first argument. So Koch knows that 0 plus n is just n and can compute that. But n plus 0, it does a pattern matching on n. And so if I do compute here, this is what I get. So I cannot just compute. How would you suggest we prove that n plus 0 is n? And you see, for this, I have to actually, let me abort this. By the way, another keyword that shouldn't appear in your homeworks. Let's say I print x plus y. This basically tells me what it means when I say x plus 1. And it says that it's a fixed point function. It's called add. It has two parameters, n and m. And this is how it works. It tries to match n, and if n is 0, it returns m. Otherwise, if n is the successor of p, it returns the successor of add of p. Now you see that, so if I have 0 plus n, and I do compute, I easily get n, and I can easily prove this theorem. But if I have n plus 0, and I do compute, I will have this case. So that's not trivial at all. So we're going to do inductive proofs. And we talked about the definition of addition. So if I do print x plus y, this is what I get. This is the library function nat.add. And it basically takes two natural numbers as its parameters, and it returns another natural number. So the type is this. Now, the way it's defined is that it first does a pattern matching on the first parameter. And if the first parameter is 0, it returns the second parameter. Otherwise, it does this recursive thing where it says if the first parameter is the successor of p, first add p to the second parameter and then take the successor of the result. So as humans, we know that addition is commutative, but Koch doesn't know that. So if I want to prove a theorem, I cannot just use my intuition and say that, oh, addition is commutative. So we will see that the order really matters. The first theorem, which is something that we proved in the last session as well, is that for every natural number n, 0 plus n is equal to n. Now, this is kind of easy by just following this definition. My first parameter is 0. And in the definition of add, I'm going to do a pattern match on the first parameter. And if it's 0, I'm just going to immediately return the second parameter. So this is a case where I can actually easily compute the result of the addition. So let's see the proof of this theorem. And we saw it in the last session as well. So of course, we're first going to do intros. And now I have to prove that 0 plus n is n. But I can just do compute. And 0 plus n is immediately computed as n. Because remember, again, this was the definition of addition. And if this first one is 0, it immediately gives me the second one. So I do compute, and now the two sides are the same. So I do reflexivity and end. Okay. Now, this was quite easy. What happens if I swap the positions? So this is my second theorem, which says for all n, of course, I want my n to be a natural number, n plus 0 is equal to n. Now, you see, this is problematic. Because if I have n plus 0, 0 is now my second parameter m here. And if I just want to use the definition of add to compute it, I will go into this recursive case. Okay, so let's do it. Let's do the compute and let's see what happens. So I want to prove this. I first say do intros so that I don't have a quantifier there. And then I say compute. This is what it computes. It says it's the result of this recursive function. Right? Now, I can try to argue about this, but it's really hard. This is much more complicated than what I already had. So I probably don't want to do that. So what would you suggest we do? Well, I can also try to do some simplification, let's say. So I do simplification. Again, it doesn't do anything because this is the second case of the definition of my addition function, which was the recursive case. So simplify doesn't know how to simplify this. Okay. What else can I do? Well, I can say, maybe let's do a case work on n. Let's destruct n, because I know that n is a natural number. So it's either O, which was 0, or it's the successor of some other number. So let's say I do destruct n, and I'm going to destruct it and call the new number n prime, and I'm going to say keep the equation as E. Okay, so it destructed it into two cases. The first case is when n is 0, and you're already seeing that this is kind of looking like inductive proofs. So the first case is when n is 0, and the second case is when n is not 0. And the case where n is 0 is easy. I just have to prove 0 plus 0 is 0. And I can just compute it, or honestly, I can just write reflexivity, and reflexivity is smart enough to know that. But now look at this. So I wanted to prove n plus 0 is n. And now I've written it in this format. So n is the next number, the successor of n prime. And so I have to prove that Sn prime plus 0 is equal to Sn prime. Okay, let's say I want to simplify this. This is how it simplifies it. So it says, because again, this was the definition of add. If I have the next number after n prime and I want to add it to 0, I first add n prime to 0 and then I take the next number of that. That's what I had written in my definition of add. So when I say simplify, it does this. Okay, so now what do I want to do? I want to say that n prime plus 0 is equal to n prime so that I can do a rewrite. So that I can say, okay, instead of this n prime plus 0 here, just put n prime, and then I will have s of n prime on both sides. And I can say, okay, reflexivity now. Okay, but the problem is I don't have that. I don't have that n prime plus 0 is n prime, because that's basically what I would need as an induction hypothesis. if I was doing an induction on n. So at this point, I have to just say abort. I cannot do this like that. But I basically need to do an induction. So let's write this theorem again. So for all n that is a natural number, n plus 0 equals n. And let's do a proof. So I'm first going to do intro or intros. Okay, now I want to prove that n plus 0 is equal to n, and I say I want to prove it with induction on n. How can I do this? I can just use this command. I can just write the tactic induction n, which means that I want to do an induction on n. So if I do induction n, it creates two goals for me. And these are basically the goals that you would expect from induction. You have the base case of the induction, and then for the second one, you have to prove that if it holds for a smaller value, it will hold for this value as well. But I like to also rename my variables when this happens. So I say, do an induction on n as n prime. Now, what does it mean when I write it like this? So let's go back here and let's remember our definition of natural numbers. So this is how we defined our natural numbers. Okay. So when I'm doing induction, I'm not really doing induction on natural numbers. That's not something that Coq understands. What Coq understands is structural induction. The idea is that the way this type NAT was created was that either I had O, and O is an element of type NAT, or I have an element that looks like this, looks like S of n, where n is itself an element of type NAT. So when I'm doing induction on something of this type, of an element of type NAT, what Coq understands is that it tells me it's either this rule or it's this rule. And you can do structural induction. You can assume that it holds for this internal parameter here, but then you have to prove that it holds for the entire thing. Okay? So that's really how the induction is working. It's not an induction on natural numbers in the way that you're used to it. It's a structural induction, but I mean, in this case, it doesn't really matter. We're doing the same kind of induction anyway. Okay. But here, when I say induction n as n prime, what I'm basically saying is that look at the constructor for this type. It could either be O or it could be S of something else. And call that something else n prime. So another way of looking at this is that the constructor of type NAT was either O or it was S of n prime, right? And I'm saying do an induction on n and consider these two cases, but I'm not going to put the names of the constructors. I'm just going to put it like that. Okay. And now I have two goals. The first goal is basically the base case of the induction, and I can just do compute, and then I can do reflexivity. That's easy. Now look at my second goal. This is much better because my second goal now also includes my induction hypothesis, right? So it's saying that suppose n prime is a natural number, and the induction hypothesis is that n prime plus 0 is equal to n prime. Now I have to prove this for S of n prime. I have to say S of n prime plus 0 is equal to S of n prime. Okay. Now, again, I can do a simplification on the left-hand side, because if I apply the rule in AND, I will get that S of n prime plus 0 is S of n prime plus 0. So I can do simplification and I get this. But look, I have this induction hypothesis here, which says n prime plus 0 is just n prime. So I can rewrite using my induction hypothesis. I can write my goal using this. So I say do a rewrite. I don't remember which direction, whatever, using this induction hypothesis. Okay, I used the wrong direction. So let's rewrite in the other direction. So you can either replace n prime plus 0 with n prime, or you can replace n prime with n prime plus 0, right? So anyway, I do the rewrite in the right direction, and now all I have is that s of n prime is equal to s of n prime, and this is just reflexivity. Okay, and QED. So we've now proven this theorem. Okay. So let's now try something similar, but with subtraction. So let me show you how subtraction works. So this is the definition of subtraction in the standard library. There is a function called sub that takes two parameters that are both natural numbers. It does a pattern matching on the first parameter. If it's 0, it returns n. If it's sk, it matches m. And then again, if it's 0, it returns n. And so. Okay. So this is the recursive definition of subtraction. Now, this is the theorem that I want you to prove. I want you to prove that for every n that is a natural number, n minus n is 0. Okay? And this is using this definition of subtraction. Okay, I'm going to give you a few minutes to get to QED on this. Did you get it? Did you get QED? Okay. Tell me, what should I do? Okay, first we do intros. So now I have to just prove that n minus n is equal to 0, and my only assumption is that n is a natural number. What should I do? Okay, induction on n. Okay, and as before, whenever I do induction, I like to rename my variable to n prime. Okay, and actually, I think I can even add the equation when I do induction now. Apparently, I can't. Okay. Okay, it's not like this, right? Okay. So we have two cases. We have the base case, and then we have the inductive step. So how do you prove the base case? Yeah, we can just do reflexivity, because reflexivity also does compute. So it computes that 0 minus 0 is equal to 0. That's fine. Now we want to prove this one. Our inductive hypothesis is that n prime minus n prime is 0. And then we want to prove the same thing for the successor of n prime. So we want to prove that s of n prime minus s of n prime is 0. So you say simplify. So we do simplify. And here's the thing. Why did this work? Why does s of n prime minus s of n prime simplify to n prime minus n prime? This is back in the definition of minus. Look at this. So this is the definition of subtraction. If n was s of k and m was s of l, then this would return subtraction of kn. Okay, so in this case, coming back to my proof, k and l are both n prime. So I have s of n prime minus s of n prime, and by definition of subtraction, that's equal to n prime minus n prime. So that's why simplify works here. Okay, but now at this point, this is just my assumption. Thank you. Okay. But instead of using assumption, actually, let me ask you this. So let's say I don't want to use assumption here. Let's say I don't have this tactic. Can you solve this using rewrite? Yeah, so I can just do rewrite using IHN prime, and I can do it in any direction. I can do rewrite in this direction, and I get 0 equals 0. I can do rewrite in this direction, and I get n prime minus n prime is equal to itself. In any case, I can just use reflexivity afterwards. And that's it. So assumption is kind of a special case of rewrite. Okay. So let me recall the definition of add. So this is how we added two numbers. We do a pattern matching on the first number. If it's 0, we just return the second number. Otherwise, if it's the successor of P, we first add P to the second number and then return its successor. So this is how addition is defined. Based on this, I want to prove this theorem. So TH5 is this: for all A and B that are natural numbers, I want to prove that A plus B is equal to B plus A. So I want to prove commutativity. Okay, try this. I'll give you several minutes. Let's do this a little bit. Of course, we first do intros so that instead of having a quantifier here in the goal, I can just bring them into the assumptions. Now, I want to prove that A plus B is equal to B plus A. It's almost impossible to do this without induction. So let's say we want to do induction. Should I do induction on A or on B? Now, normally, the rule is that we do induction on the same variable where in the definition we have a pattern matching. And in the definition of A plus B, we have a pattern matching on A first. But in this particular case, I have B plus A on the other side. So it doesn't really matter. I can do induction on either A or B. So yeah, let's just say we do induction on A. So I do induction on A, and I'm going to call it A prime. This is our induction on A. So the base case is the case where A is 0. How do we solve the base case? Okay, first I can try compute, but this is what happens if I do compute. So not a great idea. Let's do simplification. Let's see if we can simplify any side. And simplification works, but it only works for the left side. And we expected this because, again, in the definition of addition, we have a pattern matching on the first parameter. So in this case, when the first parameter is 0, simplification works very easily. But now I have to basically prove that B is equal to B plus 0. But I've already had that, right? So this is like theorem 3, B plus 0 is equal to B. I mean, N plus 0 is equal to N for any N. So I can just say apply theorem 3. And okay, you see, it can't really apply it directly. It doesn't know how to apply it. So instead, I do this. I say assert B equals B plus 0. Okay. If I do this, okay, actually I do this. I say assert B plus 0 equals B, because that's what I have in my theorem 3, right? N plus 0 is equal to N. So I assert this, which means that I have to first prove it and then I can use it as an assumption. So I want to prove that B plus 0 is equal to B. I just say use theorem 3. Now I can say apply theorem 3. Okay. And now B plus 0 equals to B is in my list of assumptions. But I want to prove that B is equal to B plus 0. So what should I do?
Rewrite.
Yes. Let's rewrite my goal using H. Now, again, I got the wrong direction. This happens to me all the time. So I do this, and now I have B equals B, and I can just do reflexivity. This was just the base case of the induction. Now, fortunately, of course, Coq keeps track of everything, so it will not forget any part of the induction. Now you have to prove this. You have to prove that if A prime plus B is equal to B plus A prime, then the successor of A prime plus B is equal to B plus the successor of A prime. Okay, so how do we prove this? Let's do a simplification first, right? Let's see which side can be simplified. and the left side can be simplified. So here what I have is that the successor of A prime plus B is equal to B plus the successor of A prime. Okay, how can I use my induction hypothesis? Yeah, so I have A prime plus B here, and I have it here too, so maybe I can rewrite it. Maybe I can get B plus A prime instead. So after this simplification, I'm going to rewrite using my induction hypothesis. And if you don't give it a direction, it will just choose the default direction. So now I have this. Now I have that S of B plus A prime is equal to B plus S of A prime. And I need to prove this for every pair of numbers A and B. Okay. So basically for any two numbers, I have to say S of A plus B is B plus, okay. So what I'm going to do at this point is that I'm going to take this part and I'm going to just define a lemma which is only this part. And I'm going to prove that lemma first. And then I can come back to the proof of this theorem and use that lemma. Okay. So just remember this format. I'm going to use the exact same format. I'm going to say I have a lemma. Let's call it lemma 1. And this is my lemma. It's for all A and B that are natural numbers, S of A plus B is equal to A plus S of B. Okay, and remember S was basically plus 1. It was the successor. Okay. Prove this one, because if we prove this one, then we can go back to our theorem and we can actually finish the proof of the theorem as well. And actually for this one, you will need to do another induction. So that's the reason why I took it out as a lemma, because I didn't want to do an induction within an induction. Like Coq supports that, but it gets very confusing. Give me the steps. Yes, first we do intros. And now we want to do an induction. Now, which variable should we do the induction on? So yes, but why is it A? Because you see on this side, I have a plus, but it's nested inside this S. The only really unnested plus that I have is on this side. And I said that generally we do induction on the variable where we did pattern matching in the definition. So in the definition of plus, I'm doing pattern matching on the first parameter. So here I'm going to do induction on A. And again, I'm going to call it A prime. I don't know what's happening here. Okay. So now I have two subgoals. I have to first prove this one, right? Which is the base case of the induction when A is 0. And then I have to prove the other side. So let's say if I can just compute in the base case. And you see that when I do compute, or actually probably even if I do simplify, I get the same thing. I just compute the both sides and I get S of B equals S of B, which can be done by reflexivity. Now I have to prove the inductive step. So this is my inductive step. Successor of A prime plus B is A prime plus successor of B. Now I want the successor of A prime plus B to be the successor of A prime plus the successor of B. So what would you do here? So what does simplify do before I do it? It will apply to the right-hand side here, right? Oh, yes. Yeah, it applies to both sides. You're right. So see how it changes the right-hand side? So this was the successor of A prime plus something. Now it becomes the successor of A prime plus that same thing. And it was also applied to the left-hand side. What do you want to rewrite? Yeah, so basically, I want to say that the successor of this thing is equal to the successor of this one. But my induction hypothesis is that the first thing is equal to the second thing. So if I just do rewrite, then I get the successor of the same thing on both sides. So I can do rewrite, let's say in this direction, of my induction hypothesis. Okay. And now, as you see, both sides are the same. Could I do rewrite in the other direction?
Yeah.
Yes, this would also give me the same thing on both sides. So after I have this, then I can say reflexivity. And this lemma is proven, so I put QED. So let's go back to theorem 5. There we did an induction, blah, blah, blah. We got to this point. So this is what we needed. We needed to say that S of B plus A prime is equal to B plus S of A prime. But I have this here, S of A plus B is equal to A plus S of B for every A and B. So it's just, I have to replace B for A and I have to replace A prime for B. Okay, so I can just write apply lemma 1. And it's actually smart enough to know how to apply lemma 1 and how to do the replacements. Okay, but let me see. Could I do it without apply? Could I do this with rewrite? So again, I can do rewrite using lemma 1. And I can also give it a direction. And again, it understands that lemma 1 is saying S of A plus B. So it understands that it has to put B in place of A and A prime in place of B. I did it in the wrong direction again. I always do it in the wrong direction. So after I do this, I can also have reflexivity here and QED. Nice. So let me give you another theorem to prove. This is our 6th theorem. I want to say for all n and m, n plus 0 times m is equal to n times n. Can you prove this? To actually prove this, you have to go back and you have to find the definition of times. So here it is. Print x times y. This is our multiplication function. And this is the definition of the multiplication function. And you see that the way multiplication is defined is again recursively. It says do a pattern matching on the first parameter n, and if it's 0, the answer is 0 because 0 times everything is 0. And if it's the successor of some other number p, then give me m plus p times m. Okay, that's how multiplication is defined. Now, using this definition, prove this theorem. So what's the simplest way to prove this? If you wanted to prove this to a human, what would you say?
Apply the previous lemma that n plus 0 equals to n twice.
Yes.
Both sides are the same.
Yeah, basically, we want to prove that n plus 0 is equal to n, so that we can do a rewrite, and then we can get our main result. So we've talked about assert before, right? So let's actually first do intros. And I assert that n plus 0 is equal to n, which means that I have to first prove this, and then I can use it as one of my assumptions. Okay, so I say assert n plus 0 is equal to n. It says prove it to me. Okay, how would you prove that n plus 0 is equal to n? You just said that we apply one of the previous theorems. Which one? This one, right? Theorem 3 says that for every n, n plus 0 is equal to n. So what happens if I apply theorem 3 here? Can I just write apply theorem 3?
No.
No. Why not? Because you see in theorem 3, I have n plus 0 equals n.
we should rewrite.
Okay. We should rewrite how?
We should rewrite n+0 as n.
Okay. So should I do another assert? Assert n plus 0 equals n. For this one, can I apply theorem 3?
Yeah.
Yes. Okay. Now that I have this, I can rewrite. Right? But I could do this without the assert. So already here, I could just say rewrite theorem 3. Right? Because I have theorem 3 and I can do rewrite based on it. And I think in this direction, I always get the direction wrong. Okay. I rewrite in this direction and it basically replaces n plus 0 with n. So I get this. And I can do it again. I can again rewrite using theorem 3. And I get n equals n. And at this point, I can finally just say this is reflexivity. Okay, but could I do it without even the first assert? So at this point already, could I say rewrite based on theorem 3? Yes. So theorem 3 says that n plus 0 is the same as n. All I'm doing here is that I'm saying take n plus 0 and put n in its place based on theorem 3. And I'm going to do it again. So rewrite again based on theorem 3. And finally, I have reflexivity. So in this case, I didn't really need to use another induction. Let me give you something else. So let's say this is theorem 7. I want to have many numbers now. So I want to say for all n, m, p, and q that are natural numbers, n plus m plus p plus q is equal to m plus n plus p plus q. Okay? Prove this. So I'm basically only swapping the first part. So n plus m is becoming m plus n.
And we apply the previous theorem.
Sure. How do you apply it?
Maybe we first assert n plus n.
Okay, first we do intros. We always first do intros. Okay. Then we assert.
M plus n equals m plus n.
Yes. We assert this. And then this was basically this previous theorem, right? So it was theorem 5. So I can just say apply theorem 5. Okay. And now I can do rewrite. But instead of assert and apply, I could also do it in one step. I could just use rewrite theorem 5. But you see, that doesn't work. So here's the problem. If I say rewrite using theorem 5, what does theorem 5 say? This is basically commutativity. It says that a plus b is the same as b plus a. But if I say rewrite using theorem 5, it doesn't know what kind of rewrite I really mean. Right? So I meant to say that apply it to this portion and this portion, but that's not what it does. You see, it actually applies it to this plus here, for example. Right? So that's the problem. If you just use rewrite, you don't have much control. I mean, you have control over the direction. You can give 2 different directions. But in cases like this, where you can do many different rewrites, you don't really get a good choice here. So instead, it's always better to just assert what you mean and then prove exactly what you mean. So you need n plus m equals m plus n. You assert it, you apply theorem 5, you now have it up here as an assumption h. And now you can say rewrite using h. And finally, the 2 sides are the same. So we do reflexivity and Q. Okay. Let me give you another theorem. This is theorem number 8. I want you to prove that for all n, m, and p, n plus m plus p is equal to n plus m plus p. So basically associativity. I want you to prove this. Prove that addition is associative. Okay, so as usual, we first do intros, of course. And since we have n on the left-hand side, let's try to do induction on n. So I say do an induction on n. So how do you prove the induction base case? Yes, let's just simplify, and the two sides are the same, so reflexivity. Okay. How about this one?
Simplify and then find what would be the dot.
Okay, so let's simplify to see what we get. We basically get that S of this thing should be equal to S of this thing, but these two things are equal according to our induction hypothesis. So I can just say rewrite my goal using my induction hypothesis. And as soon as I do this, the two sides are the same. So I say reflexivity. So that's how we prove that we also have associativity for addition. Okay, let me give you another one. For all n, m, and p that are natural numbers, we have n plus m plus p equals m plus n plus p. Can you prove this one? And of course, I will start with intros. So remember this theorem 5 that we had here, which basically said that a plus b is equal to b plus a. Use that somehow. So what happens if I rewrite using theorem 5? This is what I get. I get m plus p plus n equals m plus n plus p. So what if I rewrite using theorem 5 again? I get back to where I was. So it's not good to do it twice, but at least I did it once and it had some progress. Yeah, at this point, we want to say that p plus n is equal to n plus p. So let's just assert it. Assert that p plus n is equal to n plus p. How do we prove this? This is again theorem 5. Right, so apply theorem 5. Remember, theorem 5 was this. For every a and b, you can swap the order. A plus b is equal to b plus a. It's commutative. Okay. Now I have this in my assumption that p plus n is equal to n plus p, so I can rewrite using h. I can also choose my direction. Let's say I rewrite in this direction. Didn't work. I rewrite in this direction. Okay. And this is what I get. I have to prove m plus p plus n equals m plus p plus n. But the way the parentheses are put there are different on the two sides. Not really. So what does this one mean? This is basically we're doing m plus p first, and then we're doing plus n.
Oh, we apply previous theorem.
Yes, exactly. So in theorem 8, we said that the order doesn't matter. So I can just apply theorem 8. But that doesn't work. It says I don't know how to apply theorem 8. And the problem here is that this theorem is like the wrong way around.
Oh.
Right? So instead, I have to do a rewrite using theorem 8. And
I need that.
Now both sides are the same, so I can do reflexivity. Okay. One last theorem, and probably the hardest theorem that I want you to prove today. I want you to prove that for every m and n that are natural numbers, m times n is equal to n times n. So commutativity of multiplication. And of course, we start with intros. So prove this. You can also, again, check the way that multiplication was defined. So this is how multiplication was defined. Okay, so let's do this. Let's say I want to do induction. And again, I have a kind of a mirror image on both sides. So I can do induction on either. Let's say I do induction on n. This is the base case, 0 times n equals n times 0. How can I solve this base case? No, I just simplify. And this is 0 equals n times 0. And I had this, did I have it somewhere? No. Ooh. Should I do another induction? Okay, whatever. Yeah, but let's just do it here. Let's do an induction on n, just to prove that n times 0 is equal to 0. So first we have to prove that 0 is 0 times 0. I can do this with reflexivity. And I know that 0 is equal to n times 0. I want to prove that 0 is equal to Sn times 0. So I just do a simplify here. And Sn times 0 becomes just n times 0. Because Sn times 0 is 0 plus n times 0. And it can also compute that. And it's n times 0. And this is just the assumption. Great. So I did an induction just to prove my first induction's base case. And now I'm out. Now I have to prove this. I know that m times n is equal to n times m. And I want to prove that if I take the successor of m times n, that's equal to n times the successor of n. So what would you do here? Can we do simplify? Yes. Okay, this is what simplify gives us. It says that n plus m times n is equal to n times the successor of n. Okay, but what else do I know? I have my induction hypothesis, so I can take this m times n here and I can replace it with n times m. So let's say I do rewrite. Hopefully I do it in the right direction this time. And I apply the induction hypothesis. Okay. Now I have this. Okay.
Very close to the definition.
Yes, but let's take this out and let's call it a lemma. So I'm just going to have a lemma lm2, let's say lemma 2. And this just says that for all m and n that are natural numbers, I have this. Okay. And for now, I just write admitted here, which means that I'm assuming this. I will come back and prove it later. Let's go all the way here. So I have this, and I can just apply that lemma if I had that lemma. So I can say apply lm2 and QED. Okay, so basically what this shows is that I have a proof for theorem 10 if I can find a proof for lemma 2. Because I used lemma 2 here in my proof of theorem 10. And the proof for theorem 10 went through. So the only remaining part is to prove this lemma. So how do you prove this lemma? Of course, I start with intros. Again, the problem here is that I have n times s of m. If I had something like s of n times m, I could just apply the definition of times.
Oh, we should.
but it doesn't work that way. So we have to again do an induction here. Okay, that's a good idea. Let's do induction on N. Okay, that's the base case. What do you do for this base case? Yeah, the nice thing here is that we have zeros on the left-hand side of all of our operators. So if I just call compute here, it can actually compute the result. So let's say compute. And great, reflexivity. Okay. Now this is what I have. I have my induction hypothesis, and this is what I have to prove. Okay, let's simplify first.
If I will rewrite. Yeah, we can do a rewrite
What kind of rewrite do you want to do?
from right to left. Rewrite N times SM.
Oh, okay. So you have N times SM. You want to put this in its place, right?
Yeah.
Okay. So let's say rewrite using IHN. This direction. I'm always bad with the direction of rewrite. I never get used to this. Okay. So this is what we have. We have that S of this expression is equal to S of this expression, but the two expressions are not the same.
Just apply the previous theorem, should be theorem 9.
Yes, so we have theorem 9, which says that we have we can basically reorder these things. We have associativity. So let's say I do rewrite using theorem 9. What happens then?
We directly apply theorem. This format looks very.
No, because you cannot directly apply theorem 9. Because you see that you have an S here. And there's no S in theorem 9.
We first assert the.
No, you can just say rewrite using theorem 9. Right?
Yeah.
So it just takes this one and rewrites it using theorem 9. And now the two sides are basically the same. So now I can say this is reflexivity and QT. So this proves lemma 2. And in theorem 10, I just needed lemma 2 for everything to go through. So I've now proven theorem 10.